Hi everybody, I'm Gisele Bihina from CTICM in France, and I'm here to try to answer to a specific question regarding steel members and especially hot dip galvanizing on the one hand and pacifier insulation on the other hand. Regarding steel as a metal alloy, it is sensitive to corrosion, which gives it a rusty aspect as you can see on the picture. Of course, solutions do exist in order to prevent or avoid this corrosion, like paint or hot dip galvanizing, which consist in different steps, including a zinc bath. Steel is also sensitive to fire exposure due to his high thermal conductivity and also to the fact that steel members are often made of thin walls, which leads to a quick rise of temperature when exposed to a fire. Again, solutions do exist to avoid or to prevent this fire sensitivity, like spray protection, box protection, intumescent coating, or even concrete sometimes, which can be used in order to fill or to encase a steel member. These different solutions can be quite costly when you should keep in mind that you have to protect the steel members against corrosion. And the question may arise about a possible way to have a single protective coating against corrosion and fire at the same time. Well, a few years back, some research work was carried out in different laboratories in Europe on the basis that the surface emissivity of zinc is less than that of steel. As you know, the higher the surface emissivity of a material, the higher the temperature that it can reach when exposed to a fire. So the main outcomes of this research work was that hot dip galvanized steel members have a quicker temperature rise than bare steel members. This led to a proposal of an amendment to the fire part of Eurocode 3 and Eurocode 4 dedicated to steel structures and composite steel and concrete structures, respectively. According to this amendment, you can consider the surface emissivity of steel members as a function of the temperature. Actually, if you consider bare steel, so without any hot dip galvanizing, you should consider a constant value of 0.7 regardless of the temperature values. However, if you have hot dip galvanized steel, you have a temperature of 500 Celsius degrees at which the value changes suddenly from 0.35 to 0.7. This is due to the assumption that at 500 Celsius degrees, the zinc coating has already fully melted. So you can see that the temperature rise of a hot dip galvanized steel member is quite less important than that of a bare steel member. In order to confirm and definitely validate this amendment, additional research work was carried out by EGGA, galvanizing, and CTICM in France. And this additional research work consisted in carrying out standard fire tests on unloaded steel members. Once the tests were conducted, the results were used in a reverse method in order to assess the surface emissivity of the specimens. And also, finite element analysis was conducted in order to simulate the thermal behavior of the fire tested specimens. As you can see on the pictures, different types of specimens were fire tested. We had hot rolled steel profiles, either columns exposed on 4 sides or beams exposed on 3 sides. And we also had tubular steel columns with square hollow sections. You have here a quick view of the location of the thermocouples along the members and along and in the cross section of these members for eye profiles and for square hollow sections. The table also gives you the size, the thickness of the walls of the different profiles and the equivalent box section factors of these profiles. You can see that the value of this box section factor ranges from 30 in case of 3-side fire exposure to 230 in case of 4-side fire exposure. So the thermocouples were set on different places on the specimens. And if we have a look at the temperature curves of some specific specimen, such as IPE 400 bare steel columns and beams, you can see that considering a 15 minutes fire exposure to standard fire curve, after 50 minutes, you reach a temperature higher than 600 Celsius degrees on the flanges, on the lower flanges of the specimens and on their webs. Whereas on the upper flange, which was exposed only on 3 sides, you have a temperature that is below 500 Celsius degrees. These values were then used in the reverse method in order to get the equivalent surface emissivity of the specimens. And you can see that the values are mostly less than 0.7, which is the design value of bare steel. And this value stay above 0.5 in general. So even though they are not exactly equal to 0.7, they are rather consistent. We can have the same conclusion when we take a look at IPE 240 hot dip galvanized specimens. So you can see that after 15 minutes, the temperature can reach up to 600 Celsius degrees. And on the web and on the bottom flanges of the beams and of the columns, and when you consider the upper flange that was not fully fire exposed, the temperature stayed below 500 Celsius degrees after 15 minutes of standard fire exposure. And applying the reverse method leads this time to surface emissivity values that are lower than 0.4. So they more or less confirm the value that were proposed in the amendment to Eurocode 3 and 4 regarding the temperature calculation of fire-exposed steel members. After this reverse method application, a finite element analysis was also conducted using ANSYS finite element code and 2D 4-noded elements. The symmetry of the cross-section and of the fire exposure could enable to model only half of the cross-section in each case. We also took account of the shadow effect and of the average furnace fire curve. So you have here a picture showing you a comparison between the measured values of the temperature and the calculated values of this temperature. And in most cases, the values are quite safe. Actually, when you consider the validation criteria that are used in standards in terms of relative deviation, you can see that the 3 criteria regarding the minimum value, the average value, and the relative value for up to 30% of the values, all the criteria are met. So the model could be validated against the result from the standard fire tests. Well, all these results can be gathered on a graph, on a plot, when you can have the temperature after 15 or 30 minutes, for instance, of standard fire exposure as a function of the section factor values of different steel profiles. Well, according to this graph, you can see that accounting for hot dip galvanizing can have a significant impact on low to medium section factor values, and especially when you consider R15 fire resistance rate, which is actually used in single-story warehouses requirement in France. So for these warehouses with a single story, you must meet a R15 standard fire resistance. And the impact is all the more significant when you consider section factors ranging from 60 to 120. So in this specific case, you can have a decrease of temperature of up to 100 Celsius degrees. And if you consider bare steel or hot dip galvanized steel members and a critical temperature of 500 Celsius degrees, you can see that for a section factor of about 150, the standard fire resistance duration stays below 15 minutes. However, when you apply the amendment, you can have a standard fire resistance duration, that is higher than 15 minutes, well, slightly higher, but you can see in the specific case that it is quite unnecessary to over-design the cross-section of this member just by applying hot dip galvanizing. So in order to answer to the initial question regarding the possibility to have a protective coating against both corrosion on the one hand and fire exposure on the other hand, you can see that it can be done with hot dip galvanizing, provided you want to meet low fire resistance rates and you have low to medium section factor values. It's not definitely an alternative to existing passive protection solution, but well, in certain cases, it can be quite an alternative to usual design, traditional design. So thank you for watching, and if you have any questions, I would be delighted to answer to them.